Hello, good morning, good afternoon, good evening from wherever you're joining us across the globe. Let's It's another beautiful day for us to learn physics. We thank God for this wonderful day and for the gift of life and good health. If there is no life, we won't be here. If there's no good health, we'll be in our beds or we'll be in the hospital bed. So we give appreciation to Lord God Almighty who has made it possible, granted us the health and the strength to be here today. My name is Samuel Anekan, and I'm going to be your host. I'm going to be your tutor. So this is our series on density and upthrust, which we'll be having. This is going to be lesson 9. In our last lesson, we looked at the principle of flotation, and I explained briefly why ships float. Today I want to expand further why ships float. I want to make it clearer why ships actually float. So I would like you to get your pen and your paper so that you're going to take down notes. You are going to do what? You're going to take down notes and flow with me as we flow. So we before I move ahead, there's something I would like you to do. If you are not subscribed to this channel, I would like you to hit the subscribe button. Go ahead and hit the subscribe button and also click the like, because you are actually going to enjoy this class today. Go ahead and hit the subscribe button. Go ahead and hit the like button, because like I told you, you are going to enjoy this lesson. And at the end of the day, be ready to drop your comment. If you have any question, drop them. If you enjoy the class, tell us. If there are ways we can actually improve and help you, also drop your comment as well. So like I said, that the topic is why ships float. Why do ships float? Ships are made of iron. They are made of steel, and the density of iron is greater, far greater than the density of water. Normally, something can only float when in a liquid, when the density of that object is lower, smaller than the density of the liquid. Now the density of iron is 7,800 kilogram per meter cube, and density of water is 1,000. Density of water is 1,000 kilogram per meter cube. So the density of iron is like almost 8 times that of water. So if you put a coin, something as small as a coin, a small coin, inside water, it's going to sink. If you put a bar of iron, it's going to sink. It's going to sink. Now, but the ship is so massive, so huge. The ship made of iron floats. Why is it so? The reason is the design of the ship, the way and manner in which the ship has actually been designed. It's just the reason why the ship doesn't sink, it floats. So I'm going to explain right now. Let's take for instance right now, the density of iron is almost approximately 8,000 kilogram per cubic meters. It's 7,800, but let's just approximate it to 8,000. This is iron. Then that of water is 1,000 kilogram per meter cube. This is like 8 times. So from density of iron, that means 1 cubic meter volume of iron has a mass of 8,000 1 cubic volume of iron has a mass of 8,000. So let's assume a scenario whereby we take a volume of material of iron having this volume 1 cubic meter, and we now that mass of iron is going to have, that volume of iron of 1 cubic meter is going to have a mass of 8,000 kilogram. Okay, if we take 10 cubic meters of iron, then it's going to have a mass of 80,000 kilogram. The mass is going to be 80,000 kilogram. Okay, so looking at this now, looking at this, what can we say? That means the density of iron is still 8,000 kilogram per cubic meters of this material. When you take this volume, 10 cubic meters, the mass is still 80,000. If you divide mass by volume, you still get 8,000 kilogram per cubic meter. So now, if there's a way you can succeed for that ship to float, that means the density of the ship is actually smaller than the density of water. It's lower than 1,000. So the ship is actually designed in such a way that at the end of the day, the density of that ship is smaller than the density of water. That is how the ship is designed. Now, how is this achieved? How do you achieve this? When actually, let's assume you take 10 cubic meters of iron and you now fold it into a ship. You now design a ship with it. What is going to happen is that in the design of the ship, let's assume there's the outer body is made of the iron, the material of iron, the outer body, the bottom, the sides and all that is made of the material of the iron. Maybe the floor and all that is made of material of iron. But now there is a space here. This is hollow. There's an hollow space, a gap. Now at the end of the day, when you are not looking at the volume of this ship, the mass, we took 10 meter material, 10 cubic volume of material of iron, which the mass was of that iron was 80,000 kilogram, and we now use that to construct the ship. Okay, at the end of the day, the mass of that ship is still 80,000 kilogram, but right now the volume is no more 10 cubic meter. The volume comprises of the volume of the material of the iron, which is 10 cubic meters, and the volume of this space, this empty space, this hollow space, this also makes up the volume. And this volume now is even more than the volume of material that is used. So at the end of the day, if you look at density is equals to, the formula for density is that density is equals to mass over volume. Okay, so initially you had 80,000 for the material. The volume was 1 cubic meter. Now you've now folded it. Sorry, the volume was 10 cubic meters over here. The density is 8,000 kilogram per cubic meters. Now you now fold that 10 cubic meters of material, volume of material, into the ship. Now the mass of the ship is still the 80,000 kilogram, but the volume is no more 10 cubic meters. The volume has increased. This hollow part, the space here, comprises, also makes up the volume. The space here plus the volume of the material, the 10 cubic meters, now makes up the volume of the ship. And this space is even more than the space, than the volume of the material itself, the volume of the iron that is used in making the ship. Okay, so let me just illustrate. Let's assume that I'm just assuming, this is not a ship, but let's just assume that this is the ship now. This is the material, the iron, this one, the sides now, this is the bottom. So the volume of this material is 10 cubic meters. The volume of the material is 10 cubic meters. The mass of this material, of the iron, this iron, is 80,000 kilogram. But now this hollow, this empty space, also makes up the volume, is taken into account as part of the volume of the ship. And look at now, this empty space, the volume is more than even the volume of the material. So let's take it now that this empty space, this is 10, that this is the empty space is like let's say the empty space is about 300 cubic meters. The empty space is about 300 cubic meters. Okay. So if the empty space is about 300 cubic meters now, so now the volume of the ship, total volume of the ship is the volume of the empty space, which is 300 cubic meters, plus the volume of the material, the volume of the iron, which is 10 cubic meters, giving you a total of the volume of the ship gives you 310 cubic meters. The mass doesn't change. The mass of the material doesn't change. The mass is still 80,000 kilogram. So now let's get the density of the ship, average density of the ship. 80,000 divided by the volume of the ship, which is 310 cubic meters. So let me get my calculator and do punch. So 80,000 divided by 310 is approximately 258. Approximately 258. It's approximately 258. So the density is now 258 kilogram per meter cube. So look at it now. The density of the ship now is 258 kilogram per meter. This is far smaller than the density of water, which is 1,000. So the way the ship is designed now, the volume is greater than the volume of material. So when you now take the measure the density of the ship, average density of the ship, it's far smaller than the density of water. Okay, so that is just the reason. So the ship, when the ship is inserted in mass into water, before the ship gets completely submerged or even half submerged, it will displace a weight of water equal to its weight. It's able to displace a weight of water due to its high volume. The high volume of the ship now, this great volume of the ship will enable it to displace a volume of water equal to its weight, and the ship can actually float. So the ship can actually now float in water. So this is actually the reason why the ship can float in water, because of the design. It's designed in such a way that it can displace a high volume of water even before, as in, it will become submerged. And the average density of the ship is lower than the density of water. So this is just the reason why the ship could float, why the ship can actually float. The design, it's able to displace a high amount of water, such that at the end of the day, when you measure the density of the ship, the density, mass over volume, is smaller than the density of water. So when we're looking at the volume of the ship, we're not looking at the volume of the material used to make the ship. We're looking at the volume of the ship plus the hollow space. So now, as you load the ship, you are adding load to the ship. The mass of the ship increases. The volume is not altered. Nothing happens to the volume, but the mass increases. So the density is going to increase. So as you are loading the ship as you are loading, the ship will be moving, becoming more submerged, becoming more immersed in the water as the ship is being loaded. Now there is a safe point where the ship should not sink below. There is a safe point where ships are not supposed to sink below. So for cargo ships that are being loaded, or any ship that is being loaded, as they are loading it, they take note of that point. That point must not go below water. There is a line. That line is called the Clemson line. The Clemson line. This line must always be above water. So when they are loading and they take note that the water level is approaching the Clemson line, they have to stop loading. They have to stop loading, because as the ship is being loaded and mass is increasing, the ship will get submerged. Will start getting submerged in the water. And also, there is also a safe level, you know, that the ship is supposed to be submerged below. Like now, there's a point whereby the ship has to that level of the ship has to be below water, and there's a point that the ship should not get below water, below that level. So we have those 2 points. It is a danger. It is dangerous for the ship, as in not to get below water, below a certain depth, and it's also a danger when it goes beyond a certain depth. When it's submerged below a certain depth, it's a danger when it's submerged below a certain depth or level called a Plimsoll line, and there is also a danger also when it's too high above the distance, because now ship can easily capsize. It can easily turn over. Okay, so this is just the reason why ships float on water. The average density of the ship is smaller than the density of water due to the design of the ship, which gives it a high volume. The design of the ship enables the ship to have a high volume. The empty space now is actually filled with air. So if you take the average density of the ship, combining, you take the mass of the ship, mass of the material of the ship, plus the mass of air, then the volume of the material of the ship, plus the volume of air, or the volume of the empty space, at the end of the day, what is there? The density of the ship becomes smaller, like I've just illustrated mathematically. Okay, so this is just the reason why ships float. Okay, ships are hollow objects filled with air, so that at the end of the day, the average density of the ship is smaller than the density of water, and the ship can actually float. So with this explanation, I believe everything is clear about why ships actually float in water, and I've talked about the Plimsoll line. So I believe you've actually understood the reason why ships float. In case you have any question, drop them in the comment section. Drop your questions in the comment sections, and if you have any need for, you want to interact on me, maybe you need further questions and you need quick response, you can chat me up on WhatsApp. I need you to chat me up on WhatsApp as well. Chat me up on WhatsApp, okay? And if you need a one-on-one lesson, online or offline, chat me up on WhatsApp and we discuss terms. So we've come to the end of our lesson for today, which I believe you enjoy. You can share this lesson with your friends, and also, in case you are not subscribed to this channel, I would like you to go ahead, hit the subscribe button, hit the like button as well, and drop your comments. And it doesn't cost anything to subscribe. It's just to enable YouTube to share our video to a wider audience. The more people subscribe, this encourages YouTube to share this video to others, so as you are benefited, you can help others benefit as well by liking, subscribing, and commenting. Thank you, and bye bye. So in our next class, we will look at some calculations that has to do with the principle of flotation. Thank you.